Hey guys, today's screencast will be a two-parter. The first one will be looking at mining as a process, and the follow-up will explore what the environmental consequences of mining are. So let's look at mining. And of course, when we think about mining, Earth's crust, for example, we think of non-renewable resources. Non-renewables are those that exist in fixed quantities or stocks in Earth's crust. And while they regenerate, their regeneration time is of course quite slow, on the order of millions to perhaps billions of years, and therefore it's pretty much a finite supply that we have. Let's break those down into three categories of non-renewables. We have non-renewable metallic resources: iron, copper, aluminum. We have non-renewable non-metallic resources, right? Sand, salt, and so forth, limestone. And then we have, of course, non-renewable energy resources, including coal, oil, natural gas, and yeah, even uranium, which is used for nuclear power. So let's explore these. Let's start by looking at metallic resources. There is a life cycle, sort of a story to them, and it's pretty fascinating to see that the life cycle of a metallic resource starts all the way back with the exploration for those specific deposits, the extraction, the separation of the desired metallic element from the waste rock, the purification, and then finally conversion to the product, and then, last but not least, of course, discarding that product. And I think it's important to note that every step along the way, there are going to be environmental consequences. You can imagine the vast amounts of water utilized for each step, the copious amounts of energy that is utilized for each step, and then, of course, the waste produced that comes from each step as well. So it really begs the question, are the costs, the environmental costs, greater than the benefits that we derive from the metallic resource? And if that's the case, it begs the question, should we be using those specific resources? It's an interesting question, nevertheless. Um, as we start looking at mining, I think it's important that we have a definition for what an ore is. An ore is a rock that contains a large enough concentration of a particular mineral, more often than not a metal, that the rock can be mined and processed to extract the desired mineral. In other words, does that rock have a significant concentration of the desired metallic element? And is it high enough that it's economically viable to mine and extract and use it? For example, bauxite is a mineral. If you guys remember that from your mineral kits earlier this year, bauxite contains the metallic element aluminum. And when that aluminum is high enough concentration, bauxite is extracted and mined, and aluminum is pulled from it. So, really, the environmental consequences of harvesting ores from Earth's crust is in large part a function of the gradation of the ore itself. And we have high grade ore versus low grade ore. A high grade ore means that it's highly concentrated, so there's a high percentage of the desired metallic element in that rock compared to the waste rock that it's found in. Also, a high grade ore refers to its ease of access, right? So, in other words, the deposit is fairly close to Earth's surface, so it doesn't require a lot of energy to extract that material. Compare that to a low grade ore where the concentration is quite low, a low percentage of the desired metallic element, and the ease of access is not there. In other words, it's a very deep deposit, it's not well concentrated, and therefore there's going to be a lot of energy required to extract it. So obviously here, when thinking about high versus low grade ores, the environmental impacts are much larger and greater when we are harvesting low grade ores, because you need to pull out a lot more rock in order to get the same amount of the desired metallic element. Depending on the mineral resource or energy resource that we're extracting, and its location relative to Earth's surface, we have two different techniques that are designed to remove various resources from Earth's crust. Subsurface mining, for example, is designed to extract those mineral resources deep within Earth's crust that are not close to the surface, and surface mining is designed to extract those fairly close to the surface. Both techniques have advantages and disadvantages. When talking about subsurface mining, obviously there needs to be some sort of know-how and planning that needs to take place, a certain degree of ingenuity in order to blast out deep vertical mine shafts to create chambers and tunnels to then pull the desired material to Earth's surface. Um, when looking at that in terms of percentages, about 60% of the coal that we extract from Earth's crust comes from subsurface mining. But of course, it's going to be really expensive, right? And it's also very dangerous. You know, we've seen this in the news time and time again, where you have mining collapses and you have explosions, and of course the lethality of it all, with in terms of all sorts of respiratory illness associated with all the particulate matter floating around in these mines, where some of the miners are exposed to respiratory illness like the black lung disease, which we all know from Zoolander. So it's dangerous. However, one of the major bonuses to subsurface mining is that there's going to be a lower environmental impact. It disrupts 1/10 of the land surface compared to surface mining. And it produces a lot less waste. But it also leaves a lot of the desired element and mineral or resource in the ground. So comparing that to surface mining, we're talking about a mining technique that is used to extract those that are very close to the surface. And often there's a bit of overburden that overlies the desired deposit. And once that's removed, it can be extracted pretty quickly, and it's cost effective, and it's much more safe. You don't have to go deep below Earth's surface and put your miners at jeopardy. The environmental impacts, however, of course, are much larger. You're disrupting a much greater area of land, which would result in a lot of erosion and ultimately land degradation and water quality degradation. So there are bonuses and disadvantages to each of these. Let's take a look at subsurface mining minerals and the types of extraction. You can see here, first and foremost, you gotta start blasting your way in. You create these deep shafts and tunnels to create chambers and areas that we can extract the desired material. Like I said, a lot of coal is extracted from this. Over 60% of the total weight of our coal we extract comes from subsurface mining. Two techniques are used, and they're really distinguished from each other based on the structural supports utilized. We have room and pillar. As you can see the bottom diagram, it looks like they're extracting limestone here, but they're actually leaving large deposits of the limestone for structural support. These are the pillars kept in place, and then the remaining material is brought to the top through a variety of carts and other mechanized equipment. The other technique, in this case, is called longwall mining, and we're extracting coal here. We have these massive propeller-like blades, these shear-like blades that pass along a coal deposit and break it apart and then send it to a cart, which is then brought back to the surface. Now, no pillars are used, as you can see in this particular one, so they're using steel prop supports to provide structural integrity to the mine. Now, those supports, as they move deeper and deeper into the mine, are ultimately removed and the mine collapses behind it. Surface mining techniques include a variety of different extraction types, including open pit mining, strip mining, contour strip mining, and then finally mountaintop removal. The strategy employed is usually determined based on the type of material they're extracting as well as the local topography. I would say just about 90% of our mineral metallic resources that are extracted from mines come from surface mining techniques. So let's take a look at the different varieties. First, we have open pit mining. Open pit mining is typically Utilized when the deposit is pretty close to Earth's surface, but the desired metallic deposit runs very deep, right? And so in this particular case, they use large earth moving materials and equipment that are designed to dig deep. For example, here in Chile, one of the largest copper mines in the world, this is a massive open pit mine where, as you can see, they dig sort of a series of terraces, and what these terraces are, they're used to design to construct roadways for the equipment to get deeper and deeper and deeper as we continue to extract more and more of the desired metallic resource. Another technique commonly employed in areas that have a flat topography is what we call area strip mining. And this is fairly economical for extracting mineral deposits that lie in sort of large horizontal beds close to the Earth's surface. So, really, the first step in area strip mining is they take these massive or gigantic earth movers, absolutely incredible, and that actually strips away the overburden. So, that's the unwanted rock and soil that lies over the desired mineral deposit. And they move that, and then with a huge power shovel, and these things are massive. This is the massive power shovel, which is sometimes over 20 floors or 20 stories, comparing it to a building. Absolutely huge. They would dwarf your typical Tonka truck that you guys use in your sandboxes. And what they do is they remove the overburden and they place the overburden in a sort of a mound in the previously dug trench. And so they continue to do this, and they'll extract out the desired mineral, they'll create the trench, and then they fill in the previously dug trench with the overburden from the newly dug trench. Now, if the land is not properly recontoured and restored following it, oftentimes what is left are these sort of wavy spoil mounds, and that's just like huge piles of the overburden that are highly erodible, and oftentimes lead to significant desertification and soil erosion. In areas of great relief with lots of ups and downs and mountainous valleys and peaks, more often than not, another technique is utilized known as contour strip mining. And so, what they do is they build a series of terraces where you have these gigantic power shovels and bulldozers that cut a series of terraces into the side of the hill. Now, that exposes oftentimes seams of coal. And if they're not exposed, well, they'll have to remove the overburden. And then, once exposed, these massive power shovels will go in and pluck out those coal seams. Now, of course, in these mountainous terrains, by removing this material, more often than not, it ends up at the valley bottoms, plugging and filling in a lot of streams, degrading water quality. Here are the sort of remnants of contour strip mining in West Virginia, an area that we know has ample supplies of coal. And you can see that the landscape itself looks fairly lifeless and more like a moonscape following this technique of mining. Perhaps the most devastating form of mining, though, is what we call mountaintop removal. And this is commonly used in the Appalachians in the United States, where they literally blast the head off and decapitate mountains in order to get to the coal seams and deposits below. Following massive explosions, huge earth movers and power shovels and massive drag lines scrape over the landscape to expose those seams of coal, in which they are then removed. And obviously, a very efficient way to get to the coal seams by basically beheading the mountains themselves. This is obviously a fairly controversial mining technique that's in the news quite frequently, and we are certainly going to be exploring the consequences of it, as much of the land area and the material and overburden falls into stream valleys and causes lots of degradation to our waterways. So that's it for the mining process. Our next screencast, we will be exploring what those environmental consequences of mining are. Thanks, guys.